So I'll try and give you an idea of what will be included in this course. This is as feedback for people who found the fact that we're changing topics between different presentations a little bit jarring. So to remind you, Geant4 is a toolkit that provides all the capabilities required for particle transport simulation. I will go over these capabilities, and of course we'll remember them. You should be likely familiar with most of them, but maybe you have gaps in this knowledge. You're able to, of course, define the beam or source, what generates the particles. You enable the user can create a setup, the geometry, the materials of a setup, and a potential magnetic, electric, or other field. Geant4 itself provides physics models with which these particles will interact with this material. Many of these physics models have different options in the toolkit, and you'll hear a fair amount about these over the next days. The toolkit itself provides you the capability to track all these different types of particles, tracks of these particles through the geometry setup. And however complex it is, this was an innovation of the Geant3 toolkit, which we've carried over into Geant4. Previous generations and other toolkits did not provide this necessarily as of 30 years ago, but of course it's become a staple. It also provides the ability to the user to record information in several different ways, which we call scoring, and also in fully customizable ways, which we call hits, and provides the ability to configure how the simulation is run, to visualize it, to store output in the way of scoring and hits. It provides with templates for both simple applications and applications which are a bit more full. The toolkit comes with what we call advanced applications, which are full applications for a few key targeted areas. It comes with extended examples which demonstrate a number of features of the toolkit specifically, without giving a full example, but without trying to do everything, and with basic applications which you're probably more familiar with. And Geant4 can be built into applications for a set of problems or a community. For example, the different applications for accelerometer modeling, interactions with collimators, beam pipes, and the like. And there's also many different applications for the medical field, whether medical imaging, radiotherapy, or other. This course expects that you already know about the overall structure of Geant4. We may touch on how it's put together, where different things go, but this is mostly as a way of resituating this and trying to go in depth. We will not go over every single part to try and discuss all the key elements at the more basic level. It expects that you have written at least parts of a Geant4 application, that you have minimum working knowledge of C++, including some concepts of modern C++. No one expects you to be an absolute expert. The course will go in depth in several of these areas. It will give you an idea how a user should be able to know and control the key aspects and guide you in how to avoid some of the pitfalls. It's difficult to guide you in how to avoid all of the pitfalls or necessarily most of the pitfalls, but it certainly cannot discuss corner cases. It cannot really go into depth in every single one, or it would have probably taken 3 to 4 times and the amount of time that we have available. We hope and expect that you'll ask questions frequently about anything that's unclear, to understand how these capabilities that we discuss are applicable, how to make choices between different methods or physics models, for example, and about the difference in the strengths or maybe the deficiencies of the different options or models which are offered. We ask that you please try and use Mattermost to ask your questions, even if you're in here, and of course, if you are participating remotely. So please find the link in the email that we circulated yesterday. And for follow-up questions or clarifications, intervening by raising your hand, both in person or remotely, is requested. A rough idea of the main topics you'll have seen from the timetable. Today we start off with geometry. We talk about the framework of physics processes and models and about hadronic physics. And we have a small little presentation at the end about how to create your own customized user interface commands. Tomorrow we have the topic of external electromagnetic fields, EM physics, multithreading, and user classes. Then on the third day, fast simulation, recording information using scoring, geometry, and hadronic physics. In a second part, day 4 has optical physics and more in depth on multithreading. Day 5 has physics lists and how to bias to get results faster for your simulation, both in a general way and using physics modeling. In particular, some of the topics are covered over multiple days, in part because there's so much information that we don't want to oversaturate you with it in one go. And it also gives you a chance to, once you've digested it, to try and come back. There's also other opportunities to come back to the topics that we discuss on subsequent days. There are discussion sessions that are intermingled and a session on the final day. If after everything else you really haven't quite understood how something fits in, or if there's a question that you thought you had understood but you have significant problems with, you can come back to it then. In general, you will hear shortly the first part about the geometry, and that's a key part of how you describe your detector, but there's quite a lot of depth, so we will continue on day 2, how to describe a complicated hierarchy of volumes. When might you want to use what we call repeat volumes, how to check for errors and overlaps, and a little bit about how to import geometries from other tools. In the case of the electromagnetic field, how to define it for the setup, how you can actually try and get accurate simulation, or how inaccurate are you willing to accept the propagation or the integration of the motion in a magnetic or otherwise a field, and how can you trade between accuracy and speed. In the case of the physics processes, Geant4 has been put together in a way that software models for different physics processes are able to act on a particular particle track in a way that is flexible, and you can plug in a lot of different things, as you've already seen from this and probably have seen before. But this comes with a way of expressing them, what's called a physics process, and these act on other entities. We'll go back over what these are because they're key to understanding how Geant4 is put together, and it allows you to understand different concepts which we will need also for other topics. The process interface is a key interface in this case. So this discussion of the framework, which will be the talk after the coffee break, will go into the physics process and also give you an overall understanding, but the whole discussion of it, where electromagnetic processes fit in, where hadronic processes fit in. We do not really go into details about the decay processes, but if you want, you can ask how they fit in as well. A little bit about where the physics is in the different days. I think this is more something that you can refer back to. It's not something that you can see it also from the timetable. Recording information and using multiple threads. We've sort of semi-grouped them together, but they're spread over days 2, 3, and 4, with the small interjection of configuring your application at runtime, which is today's final talk. Multithreading also will feature tomorrow and on Thursday in order to try and give you a better handle on this rich subject. And finally, the speeding up your application. Many cases you'd like to have the results in an hour of what you might otherwise be able to simulate in a day. Is this realistic? How realistic is it? What can you do to undertake this other than using a faster computer? There are some applications for which this is possible. For other applications, it's not possible. We'll try and, this is not a topic that's trivial, but we'll try and give you a first idea and understand how to do this. I think that's okay. Areas that we do not cover in this course. Geant4 offers a built-in analysis module, which is portable between operating systems and adapted to Geant4MT, to the multi-threading mode. But the idea is that this would be useful for people who want to write a standalone application and take it in different places. If you already have an analysis package, for example, in high-energy physics route, which you utilize otherwise, you can either use it directly, or you can use what exists here to export a file, and then you do your analysis externally. We do not really talk about this. You will hear about the sensitive volumes and hits which you generate, which you can store in different ways, but you will not hear about how to do it. Visualization and user interfaces was a topic that we had a lecture on last year. We do not have one this year. And also we do not go into super depth on a number of topics. We do not cover DNA physics models at all, but that go below a few, a KV. Atomic de-excitation is touched on lightly. Phonons or channeling of particles using crystals is also not touched on. And to go back, please use Mattermost to ask questions, even in this room if at all possible. Then the person who's helping out will try to find the right time to raise the question. If it needs a quick answer, we may well answer online. If it's a yes or no, or we may understand, okay, people have not really understood quite a key concept, and we will stop and ask the lecturer to go back. In case we are distracted, please do actually intervene if you've asked the question and it's not been attended to within a few minutes, or except if you see that the lecturer has to finish some particular topic. For a follow-up question, by all means, raise your hand, as I said earlier, both in the room and remotely. If the discussion is going on, moving along, you can also just intervene. And in general, if you're trying to follow but really have become lost, do ask for clarification. There's no point in having people lost in the flow of things. As a topic develops, if you do not understand the first and second concept and you're lost, then by all means, please ask for clarification then. Finally, if there have been a lot of questions, for example, and we would prefer to try and wrap up a topic, we may ask you to keep your questions to the end. But for the moment, most of the time, we expect that you will ask questions and we will try and answer them during a particular course. So during a particular lecture, I should say. So that was basically an overview and what we asked, how we would like to have the interaction. I will stop the recording of this overview talk and we can proceed with the first presentation.